Alright, the day you have been waiting for. No more definition of a derivative. Now we get to use the shortcuts. So this notation here is saying that you are finding the derivative. D over dx is one of our derivative symbols. And it is saying the derivative of a constant is just 0. When you have a constant on the graph, it looks something like this, where it's just a horizontal line. Something that's constant. Well, there's no slope, or I guess the slope is 0. There's no rise over a run, it's just 0. So anytime you are asked to find the slope of a constant, it equals 0. That is rule number 1. Rule number 2 is called the power rule. If you have a base to an exponent, what you do, you drop that base in front of it, and then you subtract 1 to the power. So if we were to do this definition here, it would just be this rule. So in example 2, if we wanted to find f prime of x, we would drop that 5 in front, and then we would subtract 1. So f prime of x is 5x to the 4th here. Now examples 3 and 4 are a little trickier to do. It has to be a base to an exponent. So we want to change the notation of it. So anytime there are roots, that makes our exponents fractions. So I'm just rewriting f of x as x. It still stays to the power, but then the root becomes the denominator. And so now we are deriving x to the 2/3. So when we derive it, same thing. We drop the power in front of it, but then we have to subtract 1. Well, in this case, 1 would be 3/3. And so our new exponent is the negative 1/3. Now it's okay to keep it in this notation. However, if you are asked later, what happens when x is 8? It might actually be easier to simplify it. It stays 2/3, but then the x gets, you could say, the power of 1 and the root of 3. You could simplify it like that as well. So again, if you're not asked to solve any of it, I would leave it in the first notation here. But then if you're asked to plug something in for x, it's a little bit easier to do that in that simplified form. Now example 4, same thing. It has to be a base to an exponent. It does not work with a fraction. We'll learn later in this lesson what to do with fractions. So just like we did in this last example, negative exponents go into the opposite part of the fraction and become positive. Well, we could do the opposite. If we bring the exponent up, it becomes its opposite value. So 1 over x to the 4th is x to the negative 4th. So now when we derive that, we're dropping that 4. And careful, when we subtract the 1, we're at negative 5, not negative 3. Okay, so that's the power rule. Our third rule is very similar to the power rule, but it's asking, it says when we have a constant in front, we can do the constant times the derivative of what's behind it. So in example 5 here, when we're saying y equals 5x to the 7th, when we're asked to find the derivative, it's actually 5 times the derivative of x to the 7th. Well, we learned in the previous rule that we can drop the power, keep the base, and subtract 1 from it. But this would be a time where we'd want to simplify it. So 35x to the 6th. Now we could have just done that right away. We could have said, let's not separate them and let's treat it like one thing. When we drop the 7, it gets multiplied to the 5. So 7 times 5 is 35, and then subtract 1. We could have jumped there, but I want you to remember that you can keep the constant separate from it because it does come in handy later when the problems get trickier to keep the constant in front. Alright, example 6 here, similar to before, our rule only works when it's not, our exponent is not stuck in the fraction. So we're just going to rewrite this as 4/5 x to the negative 3. Because remember, when we bring up exponents, they just become their opposite value. And so now when we multiply this, or derive this, this negative 3 gets multiplied to the 4. Remember, that's like a negative 3 over 1. So then the 1 gets multiplied to the 5. And so this actually equals negative 12 fifths x to the, when we subtract 1, it will be negative 4. Again, calculus is really nice. You can leave the problem like that. We say that's unsimplified. You can leave the problem like that and it's totally fine. If you are asked to plug in a value for x though, it might be easier to see it as this, because your brain just works better with how to solve that. Okay, so these rules are really nice because we did not have to do this definition of the derivative. We were able just to use the shortcuts, and if we use the definition, we will get these values, but we love shortcuts if we can use them. So these rules also work with adding and subtracting. So rule number 4 says if we add or subtract functions, we can add or subtract their derivatives. So in example 7, you are just going to, if we want y prime, you are deriving each piece here. So you're like, oh, let me call that 3x to the power of 2, drop the power, subtract 1. Because we're adding, we can do our rule where we drop it, so that's 8x to the first power, but we don't usually write the first power. Then our next one, negative 2x, well, x has a power of 1, so negative 2 times 1 is negative 2, x to the 0 is gone. And then a constant we said derives to 0. We don't usually put the plus 0 because the constants are just 0, but you certainly can if you'd like to. Okay, then we get to some trickier problems, but you can still do this. As long as you add or subtract, you are able to derive it. So we're going to rewrite g of x a little bit, because right now we can't derive this one just yet. But we can simplify this. So we can say it's 3 over negative 2x to the 4th power, makes that negative 2 to the 4th power, so negative 2, 4, negative 8, positive 16 x to the 4th power. But I'm going to rewrite that as 3 over 16x to the negative 4 so that that exponent is not trapped in the denominator. Then this x over 2, I'm going to rewrite as negative 1/2 x. I think it's easier to see our x on its own, not stuck in the fraction, and then plus this 1/4. So now that it's rewritten like this, I want you to pause the video and see if you can find g prime of x. When you're ready, you can play it and check your answer. Alright, that first answer, negative 12/16 x to negative 5th minus 1/2 works. If you're not asked to plug something in for x, you can absolutely leave your answer that way. If you were asked to plug something in for x, you might want to simplify it to what's on the right there in green. It's a little bit easier to plug values in for x that way. Alright, example 9, you are asked to find the equation of the tangent line that goes through x equals 2 of this function. So remember, tangent line goes through one point on the function, and so right now we know that x is 2. It's given to us right here. Well, let's take a look at this note in blue. F of x gives the point. So if we are asked to find the y of the point, we have to use f of x. So let's go ahead and do that. We are going to find f of 2. And that gives us the y value of the point we're going through. Alright, when you solve that out, you do get 25. So the point we're going through is 225. But now when you're asked to find the slope, well, the slope is f's derivative. So we want to find f prime at 2. Well, we should first derive it. And so when I first derive it, I'm actually going to leave it in terms of x, and then we'll plug in 2. So f prime of x means 12x squared minus 6 when we do the derivative. And now we can find the derivative at 2. Go ahead and solve that out. Alright, you get a slope of 42. So this is the point and the slope for this tangent line. Alright, for example 10, it is really tempting to want to just jump right in, but up here we notice that our rules so far only work for either monomials, so one term, or addition or subtraction. When you get to a problem like example 10 and its multiplication, we'll learn about that in a moment, but we actually cannot derive when it's in this form. We would actually have to FOIL this out. So go ahead and do that and then play the video when you're ready. Alright, once we FOIL it, now it's all addition and subtraction. So we can use our rules that we've been doing to find the derivative of h. So give that a try and play the video, or pause it, and then play the video when you're ready to check your answer. Alright, there's your derivative. So, derivatives also work in other variables than just x and y. So in this next problem we have a cube. The volume of a cube is side cubed. And when it says find dv/ds, what that is saying is find the change in volume as the side of the cube changes. So if we were to take a cube and enlarge it or shrink it, the derivative is just saying how is the volume changing. And so all it's saying when it says dv/ds is dv/ds is equal to 3s squared. Our derivative rules work in an example like this. Then when it says specifically what happens when the side is 4, well now we're just plugging in 4 for our side and we get 48. We're not told what the units are, but let's just say it's feet squared per second, or feet cubed, I'm sorry, because it's volume. Feet cubed per second is what that label would look like. Alright, moving on to example 12. It is really tempting right now to want to call this 2x times 3 if you do the derivative of both of those. You're like, oh, drop the power, subtract 1, but do not. If it's not addition or subtraction, we'll learn what to do when it's multiplication or division. If it's something like this, you would want to call this 3x cubed. Just simplify what's in the brackets, and then when you actually derive it, you drop the 3, get 9, x to the minus 1, you get 2. See how this one would have gotten us 6x, but that was not our answer? Our derivative is actually 9x squared. So be careful, our rules only work when it's a monomial, like how we had to convert it to 3x cubed, or when it's addition or subtraction. What changes if it's multiplication and division is, if it's multiplication, it looks like this. We say it's the first times the derivative of the second plus the second times the derivative of the first. So again, this is if it is two things being multiplied. So if we look at example 13, if y is those two things being multiplied, sure, you could FOIL it out if you wanted, but that's actually doing a lot of work. So instead of FOILing it, that's where this derivative rule is really nice. When you do first times the derivative of the second plus second times the derivative of the first, this is the setup. So I want you to pause the video and see if you can get the simplified version of this. I forgot to give you this little hint. When you do the square root of something, x has the power of 1 right now, and square root has the denominator of 2. So you can do this as 2x to the 1/2. Okay, go ahead and give it a try. Alright, this is our simplification. Again, you don't have to simplify any more than this if you don't want to. If you wanted to, you could call this 1 over... Oops, sorry. Little marker malfunction. 1 over the square root of x. But you didn't have to, you could have left it as the negative 1/2 power. Alright, catch me in part 2 because this free version of this app only allows me to record 15 minutes at a time. So for the rest of the notes, catch me in video 2.